Good morning, students. We'll start with the today's lecture. In the previous lecture, we have seen the refraction of the electric flux density D at the boundary between two perfect dielectric materials that we have seen, right? And we have solved few numericals based on that, right? We will continue and we'll try to wind up this chapter by today or at the max by next class, right? Okay, the topics that are going to be covered is right. This is the last topic actually, capacitance and examples, right? Okay, we'll see the what is capacitance, the parallel plate capacitor, and several capacitance examples. A few formulas are there. We will have a look at that. And what are composite parallel plate capacitors? That also we will see. And numericals, right? Okay, capacitance, as you know, right? If I consider the homogeneous dielectric material, this material, whatever we have taken, it is homogeneous dielectric material. Homogeneous means at each and every point within this dielectric material, the physical characteristics remains the same at each and every point, right? And in this homogeneous dielectric material, let us embed two metallic conductors. This is M1, right? Around this shape. Then this is M2. They are embedded into this dielectric material, right? And this metallic conductor M1 is negatively charged and this metallic conductor M2 is positively charged, right? Okay, these two conductors are separated by some distance d, and in between them is a dielectric medium or material. So this forms the capacitance effect right here. And we can see whenever there are two conductors and in between them if there is a dielectric material, the capacitance effect will occur whether we desire it or do not require it. So sometimes it is not desired, but still due to this, whenever the conductors separated by dielectric material, capacitance effects will be appearing, right? Okay, I hope, right? This is the construction of capacitance, right? And we will define what is capacitance by mathematical equation and we'll proceed, right? The capacitance C, it is the ratio of the magnitude of the total charge on either conductor, right? The magnitude of the total charge on both the conductors on either conductor divided by the magnitude of the potential difference between the conductors, right? So if these two conductors are separated by some distance, if I want to move, let me assume I'm moving the charge, the field is in this direction, right? Positive charge to negative charge, right? If I want to move the charge, not negative charge, if I want to move the positive charge in this direction, right, from metal conductor M1 towards M2, then it is opposing, right? So some work has to be done, right? That you know, right? Okay, the capacitance C is defined mathematically is defined as the ratio of the magnitude of the total of charge on the either conductor divided by the magnitude of the potential difference between the two conductors. So C equal to Q by V naught. V naught is the potential difference between the two conductors, and this is the magnitude of charge on either of the conductor, right? Okay, this you know already. And just by looking at this, what is the unit? Coulomb per volt. But practically we will not use this coulomb per volt. We will be using farads. Farads, right? Capacitance is measured in farads. Okay, what is this Q? We'll try to write one more mathematical equation for this. What is Q? By Gauss law, we know Q is equal to closed surface integral of d dot ds. What is this d? D is equal to epsilon e, because dielectric material is there, so we are writing epsilon. Epsilon is equal to epsilon naught into epsilon r. Epsilon naught into epsilon r. In the earlier cases, just we used to write d equal to epsilon naught e. This is in free space. But here, since dielectric material is involved, d equal to epsilon e we write. And this epsilon is equal to epsilon naught into epsilon r. Is it fine? Okay. Closed surface integral of d dot ds. D is equal to epsilon e into ds. This is by Gauss law. And in the denominator, by the definition of potential difference, we can write it as minus integration of initial position to final position. Initial position is from negative conductor, metallic conductor M1 to M2, right? So initial position for E dot dl, right? We can express this way also. And we measure the capacitance in terms of farads, not coulomb per volt, right? Practical units will be using farads. Then let us see the construction of parallel plate capacitor. Let me try to write. If you, this is one of the plate here, right? Metallic conductor, right? This is, let me call it as M1 and let me call this as M2. This is another metallic conductor. And here what we are seeing is conductor surface of metallic conductor M2 and this is the conductor surface of metallic conductor M1, right? They are separated by some distance, D. So they have taken the direction here. Let me take the help of this coordinate axis x, y, z. At z equal to 0, this metallic conductor M2 is placed. At z equal to d, this distance, right? At z equal to d, the metallic conductor M1 is placed. This total distance is d, right? From here to here, right? Then this metallic conductor M1 is having the surface charge density, negative surface charge density minus rho s, and M2 is having plus rho s, right? So the surface charge density, we assume that they are uniform, right? Okay, then we know that C equal to Q by V naught. This is by definition, mathematical definition. But actually, by looking at this equation, what we will understand is this capacitance is not dependent on charge or potential difference. It depends on the dimensions of the plates, right? So that is next equation, epsilon S by D. So capacitance C is independent of the charge and the potential difference, but it is dependent on the dimensions of the plates and the separation between the plates, right? Okay, if I draw this, if I tell you this is the surface charge or this is the plate, metallic plate, so that you will not understand. If I draw like this also, you will not understand, right? So actually the plate will be like this. This is on metallic plate, right? So another metallic plate will be here. Sorry, right? They are separated by a small distance d, right? This is negatively charged, surface charge density is minus rho s, and this is plus rho s. In between them there is a dielectric material, dielectric media, dielectric will be there in between them, right? So if I look from front to top view, this is the top view. If I see like this is the plate, right? Metallic plate. So if I look from the front view, so it just appears like a line. Is it fine? They have shown like this. Okay. So dimensions of the plates. The capacitance C depends on the dimensions of the surface area of the plates. Epsilon, this epsilon is nothing but epsilon naught into epsilon r. This permittivity is nothing but it is epsilon naught is, right. This epsilon r is relative permittivity, and this is absolute permittivity, and this is constant 8.854 into 10 power minus 12, right? Okay, this d is separation between the plates and this surface area of the plate. Okay, let me take this as a this side and this side as b. Surface area is a into b, right? Okay, so the capacitance depends on the dimensions of the plates and the distance between the two plates, right? And also it depends on the dielectric material that is present in between the two plates, epsilon, right? Okay, this is simple example has been taken based on this formula epsilon s by d. So I will not concentrate much here. Calculate the capacitance of a parallel plate capacitor having mica dielectric. Yes, they have given, and its dielectric constant is 6. And plate area 10 inch square. This plate area is 10 inch square. And separation between them d is 0.01 inch, right? So surface area is 10 inch square. Convert it into meters. Just in this problem, conversion into meters is important, right? Everything should be in meters. So 10 into inch square means 1 inch equal to 0.0254 meters. So 0.0254 whole square. So it will be converted to meter. Then d 0.01 inch. Convert it into meters. 0.01 into 0.0254. That is, it will be expressed in meters. So we know this formula. Substitute here. This is epsilon r, and this is epsilon naught into epsilon r, and this is epsilon s. This is surface area already calculated here, divided by d, right? So calculate. So I will not concentrate much. This is just substitution, right? So we'll get 1.349 nanofarads. Nano means 10 power minus 9. Okay, several capacitance examples, right? If I consider the capacitance of a coaxial capacitor, capacitance of a spherical capacitor, right? We'll see all these things. So this is capacitance of a parallel plate capacitor is epsilon s by d, right? Next we want, just I'll come to this later. So capacitance of a coaxial capacitor, right? Just you take the coaxial cable also, or coaxial cable also I can write coaxial cable. So in coaxial cable also the capacitance effect is there, right? That we call it as coaxial capacitor, right? Okay, let me try to picturize it, right? Right, this is length L. Yes, the radius of inner conductor is A and radius of outer conductor is B, right? So the radius of the inner conductor is A, the radius of outer conductor is B, the length is L, right? So with this, just okay, we can get it from this basic equation. C equal to Q by V naught. What is the surface charge? We can find out and substitute here. What is the potential difference? We can apply this basic definition. V is equal to minus integration of E dot dl, and we can find out all those things. Initial position to final position, but the derivation we will not see, right? We can find out Q, what is Q, and what is V potential, and we can substitute here and we'll get this formula directly. So we'll not see the derivation, right? C is equal to 2 pi epsilon L by ln of B by A, right? Epsilon, it depends on epsilon naught into epsilon r. Epsilon is equal to epsilon naught into epsilon r, relative permittivity, and L is length of the capacitor or length of the coaxial cable. Then B is radius of the outer conductor, then A is radius of the inner conductor, right? So this you have to remember. So C is equal to 2 pi epsilon L by ln of B by A. If I want to increase the capacitance, the length of the capacitor can be increased, or else the dielectric material, the dielectric constant, right? It can be increased. I have to choose separate another material so that capacitance gets increased, right? All those things. And it is inversely proportional to ln of the radius is B by A, right? Then next, spherical capacitor. Yes, I have inner sphere having radius A. Then I will consider another outer sphere, right, whose radius is B and separated by some distance D, and it is filled. This is the dielectric material in between them, dielectric media. This is not a circle, it is a sphere, right? So let me write, this is sphere having radius A, radius B, outer sphere, separated by small distance D, right? And this is the dielectric material present in between these two metallic conductors, spherical conductors. This is the spherical conductor having radius A, and this is the another spherical conductor having radius B, right? And A is less than B, means B is greater than A, right? Okay, fine. So once again, from this basic equation we can get it, Q by V naught. What is Q, what is V naught, we can find out. Finally we will get this. So the capacitance of spherical capacitor is 4 pi epsilon naught divided by 1 by A minus 1 by B. Just you can observe here, 2 pi will come here, 4 pi epsilon, it does dependent on length, right? It's not dependent here. Divided by, no length will come into picture here, divided by, it depends on the radius, right? Here also it is depends on the ln of B by A. It is here 1 by A minus 1 by B for spherical capacitor, right? Then if we take this outer sphere, let me assume that this B is at infinity, right? If I take this outer sphere to infinity, means this is infinite, right? 1 by infinity, this will be 0. So what I will be getting, this term is 0, A will go to numerator, so I will be getting 4 pi epsilon A. So if outer sphere is moved to infinity, or it is infinitely large, then C is equal to 4 pi epsilon A. So what is this will give me? The capacitance of an isolated metallic conductor, right? This will give me the capacitance of an isolated metallic conductor, because another outer conductor is taken to infinity, right? And we'll come to this equation. The total, yes, we know that the capacitance is capable of storing energy. Why this capacitance is capable of storing energy? Means we have in between them there is a dielectric material, right? So whenever the field is applied across the capacitance, this dielectric material, then the generate dipoles are gets generated, means this dielectric material is subjected to polarization. So this process of polarization, or this polarization effect, is capable of storing energy. This dielectric material is capable of storing energy just by relative shift in their positions of the dipoles. It is capable of storing energy. Hence we say that the capacitance or capacitor can store energy, right, in the form of field in the dielectric medium. Okay, we will have that equation. For capacitance, the total energy stored in the capacitor is given by half CV square. You know this, right? This is basic, but will not go for derivation, right? So we have seen the energy density in the electrostatic field. Similar equation we got there, right? But from that we can derive this half CV naught square. Then we know that C equal to Q by V. Substitute C equal to Q by V here. Q by V. V will get cancelled. We get QV naught. Right. Next, how will get this equation? Substitute for V naught. What is V naught? V naught equal to Q by C. Substitute here Q by C. Q square by C. Half Q square by C. So remember only this equation. Other you can derive it. This and this by referring to this basic equation, right? So half CV naught square. V naught is the potential difference between the plates. C is the capacitance, total capacitance. Okay, we will solve few numericals. Find the relative permittivity of the dielectric material. Means they are asking what is the relative permittivity epsilon r. Dielectric material present in a parallel plate capacitor. It is parallel plate capacitor. Parallel plate capacitor. Write down the things whatever has been given. Then yes, part what they have given, surface area of the plates they have given 0.12 meter square. It is in meters only. The separation between the plates D 80 micron meter, 80 into 10 power minus 6 meters. The potential difference between the plates, it is given 12 volts, right? And it is asked to find out the epsilon r, and the capacitor contains 1 microjoules of energy, means WV is given. The capacitor is storing 1 microjoules, so 1 micro, 1 into 10 power minus 6 joules, that is WV. You should identify what is given, and it is asked to calculate epsilon r. So we know the formula of energy stored in the capacitor. WV is equal to half CV naught square, right? We know V naught, potential difference, 12 volts, but we don't know C. But we know surface area and the distance between the plates, so we can calculate C, right? Call this as equation 1 and go for calculation of C. C is equal to epsilon S by D. Don't use the basic equation Q by V naught, you will not get, right? So epsilon S by D, epsilon naught into epsilon R into surface area S by D. So we'll try from this, right? So the total capacitance is given here. No, it is not given. We have to calculate, right? We'll try to calculate. Epsilon naught we know. Epsilon R, I think it should be given here, because C should be, epsilon R should be known. Let me check it. This is given. Yes, from this we can, yes, we'll get in terms of epsilon R something. C we don't know. Both are unknown. We can substitute C in terms of epsilon R here, and we can calculate. Yes, this is possible. We will go ahead. What is epsilon naught? 8.854 into 10 power minus 12 into epsilon R, and what is surface area? 0.12. Then what is D? D is 80 into 10 power minus 6. So we will calculate this. C is equal to, so it will be in terms of epsilon R, whatever we calculate. So 8.854 exponential minus 12 into 0.12 divided by 80 exponential minus 6. So I am getting it as 13.281 into 10 power minus 9 epsilon r. We don't know epsilon r, right? We have to find out. So epsilon r farads. Okay, we'll substitute here in equation 1. So equation 1 implies, so what is W? W is given 1 microjoule. So I will write here 1 into 10 power minus 6. Then half into C is 13.281 into 10 power minus 9 epsilon r. Then what is V naught square? V naught is 12 square, right? So okay, we can calculate epsilon r now. So we'll calculate. So directly I will calculate. I'll take that 2 that side. So 2, right, 2 exponential minus 6, 2 exponential minus 6 divided by this entire quantity. I'll take divided by 13.281 exponential minus 9 into 12 square. Sorry, it's 12 square. So I am getting this epsilon r is equal to 1.045. So 1.05. They have rounded, that's all, right? Okay. Okay, next we will come to the important concept of this parallel plate capacitor. What is this word composite? We have to understand. We know what is parallel plate capacitor, right? So we have two plates, right, separated by small distance. We know this, right? We know this arrangement. So these two are parallel plates having separated by some distance d, having in between them the dielectric material. Okay, that is parallel plate capacitor. But what is this composite, right? The dielectric material, suppose if I have uniform dielectric material made up of same kind of dielectric constant, then that is fine. But I have some dielectric constant material having, right, I have one dielectric material having the relative permittivity of epsilon r1. I have another dielectric constant having the relative permittivity of epsilon r2. I may have third piece also, right? So if there are more than one kind of dielectric material in between the two plates, then I will call it as composite parallel plate capacitor, because the dielectric material is not uniform. They are varying in their relative permittivities, right? I hope you are getting what's the meaning of composite, right? Composite means the dielectric material is not uniform. It is made up of different relative permittivity. This material is different, this dielectric material is different, this dielectric maybe more than 2 or more, 3, 4, n numbers can be there in between the two plates. Okay, we will restrict our study here. First case, there are two cases here. First we'll study the dielectric boundary parallel to the plates. Means I can place this dielectric material same as the plates, parallel to the plates, or I can place this 90 degree, making vertically like this. I can place like this also, right? Vertically. So I can place them normal to the plates or parallel to the plates. There are two ways of placing it. So first case we will see the dielectric boundary is parallel to the plates. We can observe here, yes, this is the metallic conductor, right? Another metallic conductor is here, its shape is also right, and in between them there are two different dielectric materials. So this is one dielectric, this piece it is parallel to the plates, you can observe here, and this is another dielectric material having epsilon 1 is the permittivity and epsilon 2 is the permittivity, and this distance, total distance between the plates is d, and the width of this or the height of this dielectric material is d1 and this is d2. Overall distance d is equal to d1 plus d2, that you should be knowing, and surface area of the plate is s, right? Similarly below it is also s. These two are conducting plates, right? And you can observe here the dielectric boundary is parallel to the plates. You can observe this is one dielectric material, this is one dielectric, and this is the boundary, right? You can see this is the boundary. This boundary is parallel to the plates. If this boundary is vertical like this, then it is normal to the plates. That is second case we will see. So the boundary between two perfect dielectric materials, it is parallel to the plates, right? Okay, we can view this arrangement. There is a derivation, but we will not see, right? We can view this arrangement. If the dielectric boundary is parallel to the plates, we can view this arrangement as the capacitors are in series, right? If the capacitors are in series, then how to write? C is equal to, suppose, observe here, this will form one capacitance effect and this will form another capacitor. For this I will call it as C1, C1s, and this is C2. Two capacitance are there, so I have to add them, right? So C is equal to C1 C2 by C1 plus C2. If the resistances are in series, I will add them, R1 plus R2. Please keep in the mind, right? R total. So if the capacitors are in series, then we will add them like this. C is equal to 1 divided by 1 plus C1 plus 1 by C2. So if you take the LCM, so C1 C2 by C1 plus C2. If instead of 2, if there are 3 dielectric material in between them, so C can be written as 1 divided by 1 plus C1 plus 1 plus C2 plus 1 plus C3. If there are 4, it continues, right? So this is how we write the formula. And how to calculate C1, C2, right? We know the basic equation. What is C1? C1 is equal to epsilon 1. Surface area of the plates remains the same. So only S, don't write S1. Epsilon S by D1. So yes, this is D1, right? Next, how to calculate C2? C2 is equal to epsilon 2 S by D2. Right? You can substitute here and calculate. I hope you got it, right? Okay. So this equation I will not see because after substitution I will not see this. This is the basic equation. We will concentrate only on this. The next second case we will study the dielectric boundary is normal to the plates. We will see that. Yes, you can observe here. This is one dielectric material, right? And this is another dielectric material. And these are the plates here. This is the plate, right? This is one plate having a surface area. Instead of A1, let me call it as S1 here. So this another plate, we have metallic plate, whose surface area is S2. Instead of S2, A2, I will write S2. Similarly, there will be plate below also, right? So this is surface area is S1, this is surface area is S2, right? And we will place the dielectric material having the permittivity of epsilon 1 between these two plates having surface area of S1. And we will place another dielectric material having permittivity of epsilon 2, right? Here between the two plates. And observe here, this is the boundary between the dielectric material. You can observe this boundary is normal, perpendicular to these two plates. These are the plates, right? And it is normal here. In the earlier case, this boundary was parallel to the plates. Here, in this case, the boundary is normal to the plates, right? So the boundary between two perfect dielectric materials, it is normal to the plates. So we will see. We can see this arrangement as these capacitors are in parallel, right? One after the other. So if the capacitors are in parallel, so we will add them. C is equal to, so this is one capacitance of C1 and this is C2. So C is equal to C1 plus C2. So we know how to calculate C1 and C2, just like that. C1 is just we have seen. So epsilon 1 into surface area is different here. So I have to write S1. Epsilon 1 S1 by the height is same D only. This height is D only. Total height is D. So D. So how to calculate C2? C2 is equal to epsilon 2 into surface area of the plate 2 divided by D. I hope you are getting the difference between this C1 calculation and this, right? I hope you can see this right here. So C1 plus C2, the same thing, epsilon S1 by D, epsilon S2 by D. I hope you are getting. So whenever the dielectric boundary is parallel to the plates, it can be viewed as capacitors are in series. So we will write the equation like this. Whenever the dielectric boundary is normal to the plates, we will see the capacitors are in parallel. So we will add them, right? Don't get confused. The resistors in series and resistors in parallel. You know it, right? Difference, right? The same thing has been told here. Okay. So this C they are calling it as C equivalent, means total capacitance C equivalent. That's all, right? C equivalent. Okay, we will try to solve your numericals and we will try to wind up this chapter. Determine the, okay, time is 12, okay, still half an hour is there. Determine the capacitance of part A, what they have given, let me write it parallelly. 1 foot length of 35 B bar U, it is a business unit, we will not worry about the standard of the coaxial cable. 35 BU means, yes, it will be having 35 BU, some other number. This number indicates that cable is capable of withstanding, it is flame resistant, right? Mud resistance, all those things will be there based on this looking. So I will not, this is standard of the coaxial cable. So 1 foot length of coaxial cable, we will not worry about this number, right? So what is the length of the coaxial cable? It is 1 foot. So we should convert it into meters. So 1 foot is equal to how many inches? 12 inches. And 12 inches, right? So we should convert it into meters, right? So 1 inch equal to how many meters? So 0.0254. So we will multiply later and we will write in terms of meters. We will get how many meters. We will see it. The next, okay, let me calculate this. So 1 into 12 into 0.0254. So I am getting it as 0.3048 meters. Has an inner conductor. Inner conductor means A. It is 0.1045 inch. So convert it into meters. Just multiply 1 inch equal to 0.0254. So we will calculate this. 0.1045 into 0.0254. So I am getting it as 2.6543 into 10 power minus 3 meters. This is in meters, right? The next, sorry, as an inner conductor, this much in diameter they have given. So this is diameter of inner conductor. So A equal to D by 2. Alright, D by 2. We have to divide this by 2. So answer I got this divided by 2. So I am getting it as 1.32715 into 10 power minus 3 meters. And polyethylene dielectric. So it is epsilon R is given 2.26 for polyethylene. Dielectric media is polyethylene. And an outer conductor has an inner diameter of 0.068 inch. So outer conductor means B, diameter is given D by 2, right? So diameter, what is the diameter? 0.680 inch. 0.680 inch. Inch means convert it into meters. 0.0254 divided by 2. So this will be B. So 0.680 into 0.0254 divided by 2. So I am getting it as 8.636 into 10 power minus 3 meters. Okay, what is what they asked? Determine the capacitance. So what is the capacitance of a coaxial cable? So as far as I remember, let me write it or let me refer it. So 2 pi epsilon L divided by ln of B by A. Is it correct? For spherical, it will come 4 pi epsilon divided by 1 by A minus 1 by B. Right? So this is the capacitance of a coaxial cable or coaxial capacitor. So we will calculate 2 into pi into epsilon is epsilon naught into epsilon r. What is epsilon naught? 8.854 into 10 power minus 12. And what is epsilon r? It is 2.26. 2.26 into what is length of the cable? 0.3048 divided by ln of b by a. What is b? 8.636 into 10 power minus 3 divided by a. A is how much? 1.32715 into 10 power minus 3. So we'll calculate this. So 2 into pi into 8.854 exponential minus 12 into 2.26 into 0.3048 divided by ln of open bracket 10 power minus 3, they will get cancelled, these two, right? So ln of b by a, ln of 8.636 divided by 1.32715. So we'll close it and do it. So I'm getting this as 20.46 into 10 power minus 12 farads. So 20.5 pico means 10 power minus 12, right? 20.5 picofarads, it's correct, right? So we'll go to part B. Determine the capacitance, same thing. In part B, a conducting sphere of radius 2.5 mm covered with polyethylene dielectric layer of 2 mm thick, surrounded by a conducting sphere of radius 4.5, means this is radius of inner sphere, that is A. A is 2.5 mm. 2.5 mm means milli, 10 power minus 3 meters. Then B, radius is 4.5, I think, yes, 4.5 millimeters. Milli means 10 power minus 3 meters, right? Then polyethylene thickness is 2 mm. So this inner sphere radius is 2.5 mm, right? This is A. Then thickness of this dielectric, so it is 2 mm thick, this is 2 mm, but radius of outer sphere is 4.5 mm. 4.5 minus 2, so there is a difference, right? Is it correct? No, it is correct only. 2. A is 2.5. 3.5, yes, it is correct. Thickness is 2 mm, right? It is fine. It is correct only here. Yes, this is a spherical capacitor. It is asked. Then what is the polyethylene? It is polyethylene. Polyethylene means dielectric constant epsilon r is 2.26. Epsilon r is 2.26. Polyethylene, it is given. So calculate the capacitance. So what is the capacitance of a spherical capacitor? So we will write the formula 2 pi epsilon divided by 1 by a minus 1 by b. Is it correct? This is 4 pi should come. 2 pi is coming here, means this is 4 pi epsilon, right? For spherical 4 pi epsilon. Let me verify the formula here. Yes, 4 pi epsilon divided by 1 by a minus 1 by b. Okay, 4 into pi into epsilon is nothing but epsilon naught into epsilon r. Epsilon naught is 8.854 into 10 power minus 12 and epsilon r is 2.26 divided by 1 by a. 2.5 into 10 power minus 3 minus 1 by b, that is 4.5 into 10 power minus 3. Okay, what I will do, first I will subtract this, I will take inverse, then I will multiply with this numerator. Okay, first I will do the denominator. 2.5 exponential minus 3. 2.5 exponential minus 3 whole inverse, I am taking inverse. 2.5 exponential minus 3 inverse minus open bracket 4.5 exponential minus 3 whole inverse, right? So I got this. I'll take once again inverse 177 something I got. Once again I'll take inverse so that it will go to numerator. So inverse of this I'm getting 5.625 into 10 power minus 3 into 4 into pi into 8.854 exponential minus 12 into 2.26. So I am getting it as 1.414. C is equal to 1.414 into 10 power minus 12 farads. So 1.414 pico. Pico means 10 power minus 12. So B is over. Next part C. Two rectangular conducting plates 1 centimeter by 4 centimeter. Part C. Let us read the question first. Two rectangular conducting plates 1 centimeter by 4 centimeter with negligible thickness, between which are three sheets of dielectric, each 1 centimeter by 4 centimeter and 0.1 mm thick, having the dielectric constants of 1.5, 2.5 and 6 respectively. Okay, we'll see this. So parallel plate is parallel plate capacitor, right? So it is better that let me draw this structure so that it will be helpful for me. Right, so this is 1 centimeter by 4 centimeter. So this is one metallic plate and below also there is a metallic plate. In between there are three different dielectric materials. So I will divide it into three, right? So this is one dielectric material and this is another dielectric material. Totally three are there, right? I hope you are getting. They are also 1 centimeter by, I think, yes, same it is 1 centimeter by 4 centimeter, right? 1 centimeter by 4 surface area. Okay. This, let me call it as D1, D2 and this as D3, right? But the thickness is same. It is 0.1 mm only. 0.1 mm. 0.1 mm. So here let me call it as D. D is equal to D1, that is equal to D2, that is equal to D3. That is equal to 0.1 mm. So let me write it in terms of meters. 0.1 into 10 power minus 3 meters. Okay. Then dielectric constant. This is they are given having dielectric constants of 1.5, 2.5, 1.5, 2.5 and 6. Okay, let me call this as epsilon R1, epsilon R2, next epsilon R2, next epsilon R3. So let me take one by one. This is 1.5, this is 2.5 and this is 6, right? These are the dielectric constants. Anything we have missed out? Next, okay, three sheets. Okay. Just observe the boundary. This is one dielectric material. The boundary is parallel to the plates or not? It is parallel to the plates. So C equivalent we want to find out. C equivalent is equal to, this can be viewed as the capacitors are in series. Right? Series means don't add C1 plus C2 plus C3 here. So it is not like the resistance 1 divided by 1 by C1 plus 1 divided by 1 by C2 plus 1 divided by C3. Is it fine? Yes. Okay, we'll calculate C1, C2, C3 separately and we can substitute and we can calculate. That is one way. Or another way is, okay, we'll calculate separately and write it. That would be better, I think. Right? So C1 equal to uh, epsilon 1, because permittivities are different, right? So epsilon 1 into surface area is same, yes only. And distance is D only in this case. D1 also if I take it is D only. All are same here. So it is D, right? Or D1 also I can write, no problem. And similarly, okay, we'll substitute. What is epsilon naught? Epsilon 1 is equal to epsilon naught into epsilon R1. Is it fine? So let's write it here. Epsilon naught is 8.854 into 10 power minus 12 into, what is epsilon R1? Epsilon R1 is 1.5 into surface area we will calculate. We have not yet calculated. It is 1 centimeter by 4 centimeter, right? 1 centimeter by 4 centimeter. So 1 into 10 power minus 2 into 4 into 10 power minus 2. Let us convert it into meters, right? Minus 2. Okay, 4 into 10 power minus 4 meters. Okay, we have calculated 4 into 10 power minus 4 meters divided by D is how much? 0.1 into 10 power minus 0.1 millimeter, right? 10 power minus. Similarly, C2 equal to epsilon 2 into S is same divided by D. It is also same. So 8.854 into 10 power minus 12 into what is this epsilon R2? It is 2.5. Instead of 1.5, you are writing 2.5 here. Only this thing will vary, right? And surface area remains the same, divided by 0.1 into 10 power minus. This is same D, right? Similarly, we calculate C3. Epsilon 3 S by D. So 8.854 into 10 power minus 12 into S. What is dielectric? 6. It is 6 here. Only this is changing. Divided by 0.1 into 10 power minus 3. So I will calculate all three parallel at a time, because most of the things are common, only this thing. So leaving this, I will calculate everything, just I will multiply this and write. So I will take in the numerator 8.854 exponential minus 12 into, I will leave this because I will multiply later I will leave this, right? I will multiply this and divide this, and then I will multiply 8.854 into 10 power minus 12 exponential minus 12 into 4 exponential minus 4 divided by 0.1 exponential minus 3. So this I am getting it as, just I will write it here for my reference, 35.416 into 10 power minus 12 into this dielectric constant 1.5. So that this remains the same for others. Just I will go on changing this, right? And I will write. So 35.416 exponential minus 12 into 1.5. So I am getting it as 53.124 into 10 power minus 12 farads. Similarly, just I will multiply 2.5 now. Next, instead of 1.5, just I will multiply, instead of 1.5, I will multiply 2.5. So 2.5. So I will write it as, I am getting it as 88.54 into 10 power minus 12 farads. So next, instead of 2.5, I will multiply 6. So 212.496 into 10 power minus 12 farads. Okay, we will calculate C equivalent. It is equal to 1 divided by 1 by C1 plus 1 by C2 plus 1 by C3. First I will calculate denominator, then I will take inverse, right? So I know 1 by C1, right? So I will take inverse. So 53.124 exponential minus 12, its inverse, plus C2 is how much? 88.54 exponential minus 12, its inverse, plus next third capacitor C3 212.496 exponential minus 12, its inverse. So I will add all the three, then I will take whole inverse, so that I will get the final equivalent capacitor C equivalent. So it is 28.715 into 10 power minus 12 farads. Pico, 10 power minus 12 means pico, 28.715, right? 28.715 picofarads. Is it fine? I hope. Yes, we'll continue with the next problem if time per last 10 minutes is there. So let me stop here only, I think. Okay, because 2 more problems are there. This will take some time. Okay, I'll stop here only. Or else, okay, I'll take up this. Okay, let me take up in the next class.